Okay, now is for the fun. So we have one SP, or one kidney bean, facing this way. I'm trying to draw in my kidney bean. And there's that little piece of corn right there. So one kidney bean is facing that way. And it's going to overlap with the 1s1 of the hydrogen. They each contribute 1 electron. And that's how we get our pair. And that overlap between the SP and the S, that overlap is called a sigma bond. If I start to go too fast, just let me know. Since the camera's on me, I get a little excited. You know, all that creative energy. Start to go a little too fast. So we have overlap creating 1 sigma bond, and then on the other side, Alicia, we got the same thing. The other kidney bean is the second kidney bean. It's facing the other direction. Isn't it? And it's overlapping with the other 1s1. And they each share an electron. And that overlap also is called the sigma bond. Yep.
What about like the two beans overlap? Does that do anything?
Nope, doesn't move. Because actually, if I drew it right, well, yeah, if I drew it right, they should be very close but not overlapping.
Shrubs?
Yep.
What about like the second little circle by the kidney in your other?
The little piece of corn.
Why is there only one?
There's 2 of them. The other one's behind there. You can't see it. But it's there. It'd be like dotted in. Behind it so you can't see it. What? We'll get better at it. So that's an example of a hybrid orbital, an sp overlapping with an s. So any questions before we move on to another example? Yep, Carrie.
So yesterday you put hybrid plus hybrid. Is it the same even though you changed?
No. We should have, that's not that at all. We should do this one before we do a hybrid. Tomorrow, we'll cover a hybrid and a hybrid overlap. A hybrid and a hybrid overlap leads to a double bond or a triple bond.
So
Correct. I'm sorry about that. All right. Can I erase this?
not yet.
I'll erase this though.
Yeah, you can erase it now.
All right, our next example, still an example of a hybrid and an S or P overlap. We're going to do boron trichloride. So before boron bonds, this is its atomic configuration. So it's in group 3A, so that's why it has 3 valence electrons. How many unpaired electrons do I have there, Haley? Just 1. So then I'd expect boron to form 1 bond. I only need 1 electron to find a pair. But the boron is bonding with 3 chlorines. So how the heck does boron form 3 bonds when it has only 1 unpaired electron? We do the same thing as we did with beryllium. When the chlorines come near, the electrons get excited. And they unpair by jumping to higher levels. Then we circle all the orbitals that contain electrons. And then we hybridize. So let's go back to our color expert. So, Kenzie, you said that if I mix yellow and blue, I get what? Green. 1 part blue, 1 part yellow, green. What if I mix 1 part yellow, 2 parts blue?
Green still, isn't it?
It's green,
It's more blue than green.
so like a turquoise green.
Yeah.
All right, so same principle here. I'm taking 1 sphere, but now 2 dumbbells, and merging them together. And the shape I get out is like that. So 1 sphere, 2 dumbbells, and what I get out are 3 orbitals. They each pretty much look like the SPs. Kidney bean and corn, kidney bean and corn, kidney bean and corn. The only difference is I get 3 of them, and they're all 120 degrees from each other. And we call them sp2s. So Allison, how many s orbitals did I circle over here? Just 1. How many p orbitals did I circle? 2. That is why it's called an sp2. They changed the terminology on us. The 2 no longer refers to the number of electrons. It refers to the number of orbitals we circle. Since I circled 1, 2, 3 orbitals total, I draw 1, 2, 3 lines. I have 1 left over p orbital. They will become important when we do double bonding, the leftovers. But for today, that p orbital is not important. I have 1, 2, 3 electrons. They go in the 1, 2, 3 sp2 orbitals. So let me just reiterate here, Callie. For atomic orbitals, we go 1s2, 2s2, 2p5. The superscript refers to the number of electrons. For molecular orbital bonding, the 2 refers to how many orbitals we merged. We merged 1, 2 of them. It does not refer to the number of electrons anymore. So, based on this here, Brittany, how many more electrons do I need for everybody to be paired up? For everybody to have a pair. I need 3 more. 1, 2, The P can stay empty. So we need 3 more electrons for a total of 6 with 3 bonds. This? Yeah. And if we check on appendix F, sure enough, group 3A, the boron family, wants a total of 6 electrons with 3 bonds. So hybridization explains why boron follows the rule of 6. Any questions on that one? Should we draw it?
Yeah.
No. It actually gets, at this point now, it gets too complicated. Because we would have 4 atoms, we'd have to draw 4 axes, and they're all not in a row, they're in differing planes. So it would get pretty tricky, so. So on Friday and Thursday, you're going to build these molecules using styrofoam balls and toothpicks.
Can't wait with it.
Thursday, Friday. So if you're gonna be gone Thursday or Friday, you need to see me, after class so I can get you the handouts. All right, another example of a hybrid and an SRP, good old methane. For our British viewers out there, I have a few. I make them feel included. Go United Kingdom. Yes?
Are we gonna be drawing this one or
No, we won't be drawing any. Tomorrow we'll draw a double bond or a triple bond, but the rest of them we can't draw, they just a little too complicated.
Okay.
All right, so, carbon starts off like this. And you look at it, you think, oh, carbon wants 2 bonds. But it's got more than 2 bonds, it's got 4 bonds. So how does carbon have 4 bonds? Well, let's do what we did with the other 2. The electrons get excited. Two of them, well not 2 of them, one of them jumps off. And now we have 4 unpaired electrons. I circle all my orbitals that contain electrons, and then I hybridize. I mix them. So how many orbitals did I circle there, Melissa? 4. So how many lines should I draw here? 4. What should I call these new molecular orbitals? How many P's did I circle? 3. So sp3.
So the like superscript or whatever is how many p orbitals you do, not how many in general.
Correct. How many p orbitals you hybridized? And these look pretty good.
Okay.
Get out 4 of them, and basically they look like a dumbbell where one lobe is really bigger than the other. So this is what an sp3 looks like. And there are 4 of them. There's one. There's a second one. There's the third one. And here's the 4th one. So there's 4 of them, and they're all orientated 109.5 degrees from each other. And so it yields a shape like that. That's the shape of methane. And because of that shape, methane is a gas, not a liquid, at room temperature. So if we fill our electrons in, 1, 2, 3, 4. How many more do I need, Kim?
4.
I need 4 more. 1, 2, 3, 4. So we need 4 more electrons for a total of 8 with 4 bonds. We'll do 2 more of these, and then I'll give you some time to work on your homework. Your homework won't take you that long, except for the reading. That will take you a long time. Okay, how about we do this one? Sure, why not? Ammonia. So, what was methane, CH4, was that a solid, a liquid, or a gas?
Gas.
Gas. At room temperature. So this one was a gas. NH3, any guesses?
Liquid.
Well, the whole point of learning the shapes is the shapes will predict the properties. So we start with nitrogen, before it bonds, being 2s, 2p, doop, doop, doop. I have 3 unpaired electrons. So I would assume that I would need 3 more electrons to bond up. And that is what happens. We don't have to hybridize to explain why nitrogen forms 3 bonds, because it does. But you can still use hybridization to explain it. You don't have to use it, but it works either way. Because if we excite the electron, it's going to jump up into the P. And when it does this, I still end up with 3 unpaired electrons. Yep.
When you're excited, is it always just one electron that'll jump up?
No, not always. It's just
How do you
that
determine?
it's just that so far we only have 1 pair.
We wrote exciting.
What?
Exciting.
Excite.
Oh. Isn't it supposed to be excited?
Oh,
Doesn't matter. It could be exciting, excited, excite. And then if we hybridize, I'll end up with sp3 hybridization because I have 1, 2, 3 p orbitals and 1 s. But now I have 2, 4, 5 electrons. So I put 1 electron in each orbital before I double them up. And how many unpaired do I have? 3. So basically, the beginning and the end are the same. We started with 3 unpaired, we end with 3 unpaired. So I'm going to need 1, 2, 3 more. For a total of 8 electrons with 3 bonds. And yes, it still matches up with Appendix F. The nitrogen family wants 8 electrons, 3 bonds. Any questions before we do our last exam? Yep, Melissa. You wouldn't have to, but, you know, it's probably easier for you if you just do it for all of them, because then it gets ingrained into your head. And then you don't have to worry about, when do I do it, when I don't do it, because it works for all of them. All right, last one, let's do sulfur. Let's do sulfur dichloride. So before it bonds, sulfur is 3s, 3p. And now when I excite it, I have 2 pairs. And when I excite it, I'll still end up with 2 pairs. It's just that my 2 pairs are now in the P. When I hybridize Alish, I circle all the orbitals that contain electrons. So I'm going to end up with sp3 hybridization. 1, 2, 3, 4 lines because I circled 1, 2, 3, 4 orbitals. I have a total of 6 electrons. I put 1 in each before I double them up. So how many more do I need, Carly? I need 2 more. 1, 2. Need 2 more for a total of 8 electrons with 2 bonds. So 2, 4, 6, 8, a total of 8, and I get them from only 2 bonds. And does that match with Appendix F? Oh, you bet it does. There's good old sulfur, right? Follows the rule of 8 plus 2 bonds. But then sulfur also has another little twist to it, doesn't it, John? Sulfur can follow the rule of 8 and 2 bonds, or sulfur can follow the rule of 12 and 6 bonds. So how is it that sulfur can follow the rule of 12 and 6 bonds? Oxygen can't, but sulfur can. And the difference, Jenna, has to do with which level they're in. Okay? Oxygen is in the second energy level. There are no d orbitals in the second energy level. So oxygen can only follow the rule of 8. But sulfur is in the third energy level. And in the third energy level, the d's exist. So now we're going to do the other option, sulfur hexachloride, and now we're going to draw on the d's.
you draw it for like when you hybridize the ones you just erased, I thought you do the amount, like you draw the lines for the amount of electrons that are in the field.
The number of orbitals that are in the p level, not the number of electrons. So if they're, the highest you can have is p3, because the maximum we have is 3 p orbitals.
Right.
But you could have 6 electrons in those p's.
Oh.
So the number of lines corresponds to the number of orbitals you circle.
Oh, okay.
So, this is sulfur. The D's exist, but they're empty. When I excite, I'm going to kick both pairs up into the D. So if someone had asked, is it always going to be one pair? Here's an example of where it isn't. This electron is going to get kicked up, and so is that one. I'll end up with that. Now I hybridize. I circle all the orbitals that contain electrons. And how many s orbitals did I circle, Alicia? How many s orbitals did I circle? How many p's?
3,
And how many d's?
2.
2. So this is sp3d2 hybridization. What does that look like? I have no idea. Though I bet if we Googled it, we could find the shape of an sp3d2 hybrid. So, how many orbitals did I circle here, Callie? 1, 2, 3, 4, 5, 6. So that means how many lines should I draw here?
6.
6. That's it. And I have a total of 6 electrons, so I put 1 in each box. And now, how many more do I need, Elish, so that everybody has a pair? 6. I need 1, 2, 3, 4, 5, 6 more. So I need 6 more for a total of 12 electrons with 6 bonds. I'm gonna pause it for a second, Riley.